folks, and welcome back. It's been a while since we have made a video, and in today's video, which is unfortunately going to be quite long, so you have been warned, this video may involve long periods of me rambling on about non-related subjects, and may also include long and boring technical explanations. So if you would prefer, there's lots of funny cat videos out there, so don't feel bad if you need to tune out. Now, with that said, before we get into the meat and potatoes, I should warn you that I have kind of a throat problem, and I wasn't able to speak for quite a few days there, so I'm only just regaining my vocalizing abilities. So if I cough, wheeze, fart, have to cut the video in the middle or something, you've been warned about that too. So, alright, let's get straight into it. We need to talk about the Tesla small drive unit open source logic board and the recent craziness that went on around that. So last time that we left you guys, I had given you a kind of explanation about what the background had been to the current problem. I'm not going to go through that again, as it'll make this video hours long instead of just 1 hour long. So if you haven't, I recommend having a look at the preceding video that I did about this particular problem. Now, so at that point, I was waiting to see if I could get medical approval because of my heart issues. If I could actually travel to, drumroll, Romania, some 2,000 miles away, to see if I could help out the guys there with their racing car. Unfortunately, I did get approval with some caveats, and I was able to travel, and I spent a week in Romania, which is a lovely country, fantastic weather, and very, very nice and welcoming people. We also learned a hell of a lot about the problems, got some good insights on where we needed to go to solve them. So yeah, it was very much a team effort, despite me not being a team player. So big thanks to the guys there, and to Johannes for all of the wonderful software work. Now, so there's three things that we were faced with. Number one was we had exploding inverters. Number two was we didn't have very good control over the particularly the current that was being delivered to the motor. And number three, we weren't able to get the full power out of the inverter. Now, I'm pleased to say that as of the making of this video, subject to final testing, all of those things are basically solved. So this is the video that I really did want to make, where I would have a solution for you guys. So let's look at the inverter failures first. Now, when I say exploding inverters, that isn't driving along, boom, flames, zzz, we're not quite talking about that. What we're talking about is failure of the IGBTs in the power stage. Now, you may recall from the video and the live stream that I did after it that I was focusing in on two things as being the potential cause for the inverter failures. Number one was the switching frequency, and the second one that I didn't actually mention because it just sounded a bit crazy, but it actually I think pretty much has turned out to be the cause, is the way that the inverter shuts down on detection of an overcurrent event. So when I got over to Romania, I had brought my own small drive unit inverter, and we went ahead and fitted that to the vehicle. I made two immediate changes to the way that we were driving the power stage. The first one was I changed from 8.8 kilohertz switching frequency to 17.6 kilohertz. Quite a big jump, but I'm pleased to report that the inverter works very, very well at 17.6 kilohertz. And the second thing that I did was I changed the trip mode parameter. Now the trip mode parameter lets one do three things. Sorry, I should clarify. Trip mode comes into play when a overcurrent event is detected by the hardware overcurrent detection circuit, and it basically tells the microprocessor what to do when it gets a hardware overcurrent detection. The first, which is the default, is called all off. And what that means is that when you detect a hardware overcurrent event, you always shut down the IGBT drivers anyway. But what you do then is you shut off the main contactor and shut off the pre-charge relay. So that's the default condition. The second choice is called pre-charge on, and that's the one that I have elected to use and in fact did use. Excuse me. Pre-charge on basically means that you dump off the main contactor, but you leave the pre-charge relay on. Now there's a third option, is called all on, which leaves on the main contactor and the pre-charge, but basically shuts the power stage down. So with pre-charge on selected, I can comfortably say that during the week that I spent with the vehicle, we triggered at least 200 overcurrent events during testing, during all manner of driving, be it on the road, be it on just axle stands, dynamometer, racetrack, everything, and the inverter did not fail. So I'm pretty confident that by using those two settings, one can avoid any inverter failures in the small drive units. Now, the second problem that we had was, how do we safely limit current? And this is something that applies not only to the whole Tesla sphere, but to all of the inverter designs based upon Johannes Hubner's system. Now, our Team A friends had informed me prior to them not talking to me anymore that they had implemented a cycle by cycle current limiting system in the inverter firmware. So because prior to us doing a lot of the testing, we weren't really sure about what was causing the inverter failures and lack of power and so forth. I believe that it was, and I still do think it's a very good feature to have a cycle by cycle current limiting system in the inverter software. So Johannes went off and he indeed did that. So I think I was at most a day over in Romania when he had made that software available to me, and we were able to load that into the vehicle and had a absolutely perfectly functional cycle by cycle current limiter. Now, the second problem then manifested itself very, very quickly, and that was the drivability of the car. Now, recall that up until my visit to Romania, the most testing that I personally had done with the small drive unit was running it on the bench, and I had no feedback really from any customers until such time as the two teams, as I call them, basically contacted me to say, oh my god, you know, we've got inverters failing here. So by the time we got down to doing some pretty serious road testing of the car, it became apparent to me that there was something very, very strange either about the motor or the drive unit in general or something, because I spent hours trying to tune the vehicle to just drive normally, and it was next to impossible. We could tune it to run reasonably well at low speeds, or we could tune it to run reasonably well at high speeds, but not both at the same time. And this was really perplexing to me, because there's one of the if there's one of the really big strengths about the Hubner inverter system is that you don't have to spend ages tuning it. You know, these things just, there's literally about 3 parameters that you really need to concentrate on, and then the motor just basically runs. Now you can tweak stuff to, you know, tune where the power comes in, when the power comes in, how fast the power comes in, all this, but the basic getting it running is quite straightforward. So this was very, very strange, and I had a very long and frustrating day, and I basically walked away at the end of the day because I was just wrecked tired. So the guys had a very productive discussion with Johannes later that night, and basically what came out of that is that the way that Johannes was reading the encoder, so the two channel encoder, was causing problems in the way that the firmware estimated the rotor speed. And for some reason, this was very, very evident with the small drive unit. I can't really say why. Maybe down to just the design of it, you know, the fact that it's smaller than the large one, I cannot say. But Johannes anyway got to work, and in his usual way, vastly simplified a highly complicated problem. And by the time I was getting breakfast the next morning, he had shot over a version of software to me, and we pretty much put that software in, and almost immediately was in a position to tune the vehicle. and there was some problems with, you know, various hardware issues around programmers and things like that. But we then got the vehicle onto a dyno, and we started tuning it. And we had overcame the initial tuning problem, which was when the vehicle literally just would not drive properly. It was just shaking, juddering, all that. So all that went away with the new encoder software. So next problem that we had was that when we're on the dyno, we couldn't really get the power up, because every time that we attempted to raise the current, every time that we tried to inject more than about 700 to 800 amps of peak current into the rotor, we would trigger an overcurrent shutdown. And my initial feeling was that what was happening was that the cycle by cycle current limiter, which works in software obviously, was either not working above 700 to 800 amps, or was not quick enough to catch some mysterious current transient that was being caught by the hardware overcurrent detection circuit. So we had a car now at this stage that drove with pretty low power, like probably about half the power that we would have expected it to be, you know, less than 100 kilowatts from the battery. So because there was competitions and stuff going on, we had to abandon the tuning at that stage. But I was still not 100% satisfied. So once some of the competition stuff had been finished up, I asked the guys to leave me alone with the car for a few hours so that I could kind of try to work out in my own way what was going on, because I suppose I'm used to working alone. Like I work here pretty much on my own, and I find that I can get distracted and confused quite easily. Now that's my problem, it's nothing to do with anyone else, but when there's a lot of talk and a lot of ideas going around, I can find it hard to, you know, focus and to stay stay locked on to one particular idea. So anyway, rambling. So I took the car out and I found myself a loose gravel surface. Now the reason for that was that at this point I still wasn't 100% sure that what was killing the inverters had been actually solved. So the loose gravel worked as a kind of a mechanical fuse, whereby if the power came on really, really quickly, it would just break the wheels loose and avoid any large amounts of excess power being delivered to the inverter. I spent about an hour tuning the vehicle, and at this point I was running with the overcurrent trip, so the hardware overcurrent trip, set at just under 1,000 amps, and the software current limiter set at about 700 to 750 amps. Now when I'd been tuning, I should just explain why. At this stage, one of the things that we had discovered was that the guys had discovered was the transistor that's used in the small drive unit inverter. So let me just jump on the computer here and I'll get that part number for you guys. Didn't mean to have it written down, but like all these things, of course I didn't. So the part number for the IGBT is the AUIR GPS 4067D1. And there are 6 of them per switch. So 6 on each, you know, there's 6 on the high, 6 on the low, times 3, right? So there's 6 transistors connected in parallel on each switch. And they have a nominal current rating of 120 amps according to the data sheet. So I was working on an assumption that would later prove to be false, that the maximum current that one could drive per phase was probably less than 1,000 amps. And it's like these things, sometimes they can be very frustrating because of course there's people out there that know this, but the last thing they want to do is tell me. But anyway, too bad, because guess what? I figured it now. So, had the car driving, well, it wasn't really driving like a racing car. And again, kind of maxing out at less than 100 kilowatts. And I'm thinking, okay, because I had similar experience with the large drive unit, and it wasn't until that I turned up the current limit that I actually got power from it. Because believe it or not, now the Panzer is running with a current limit value of 3,000 amps. And the Panzer, you know, hasn't blown up, right? Fortunately. So, I'm sitting in the car there and I'm, you know, I'm kind of stressing it and I'm saying, right, okay, alright. I said, right, let's do it. Changed over current limit to 2,000 amps and dropped the hammer. Guess what happened? Go on, take a guess. No, the inverter didn't blow. Car didn't drive any faster. And we tripped out. I'm thinking, wow, that's a bit strange. So next thing, we started doing some high-speed graphs of the peak current. And despite my having the current limit set to 2,000 amps, we tripped out at in or about 900 amps. We're talking, wow, that's strange. And of course, I'm not trusting the instruments, right? I'm doing like the pilots that fly themselves into a mountain. And I'm thinking, no, what's going on here now is there's some fast transient that the current sensors pick up, the analog circuit is fast enough to see it, and it's shutting down. And I thought, okay, alright, do it, Damien, come on, you can do it. Current limit, 3,000 amps. I'm thinking this is definitely going to blow the tar out of the inverter. Drop the hammer. Guess what happens? Same again. 900 amps. Bang. Shut down. Something very weird going on here. Set the current limit to 5,000 amps. Same again. 900 amps. Shut down. Set the current limit to 50,000 amps. You guessed it. 900 amps. Shut down. Set it to 65,535 amps. 900 amps. Shut down. we've got our real problem. And I did this probably over 2 days, like an evening and a morning, probably at least 100 times. So if the inverter were going to flip out, I would like to think it would have done so. So now we know what our problem is, right? Our problem is that our analog current sensor circuit is not doing anything wrong, and our cycle by cycle current limiter isn't doing anything wrong, because if you set the cycle by cycle current limit to 850 amps, you could drive the car all day long. Okay? You set it to 900 amps, it shuts down because it trips the hardware. But at 850 amps, it's sufficient to keep the current peaks below the trip point of the analog circuit. Now, this is a bit of a aha moment, right? So, got myself back home, left the car running at the kind of low power level, and sufficient to do what it needed to do, and got myself back home, where I've been now the last few days, and started working on replicating on the bench what's been actually going on. So next up, I'm going to show you guys what we've got and what was actually causing the problem, how we've fixed it, and how we're planning to test it. Alrighty, so I hope you guys will be able to see this. Well, this is the transistor that Elon, our old chum, uses in the small drive unit. And one of the things that I want you to see here, let me just scroll this down a bit. So, collector emitter voltage 600 volts, continuous collector current, which is, this is the thing you have to be careful of, because these are package limited and silicon limited values, but the maximum continuous collector current is 160 amps, and nominal current, which is the one I tend to trust, is 120 amps. So just a little bit of background on the transistor for you. That data sheet's available, and I'll put a link to it in the description. Now, let us now focus in on the bench here. I'm going to show you guys what we've got going on. So what I have here is a small drive unit logic board. This is the version 2, so this is the one that people have been using. It's the one that is in the vehicle over in Romania, and the one that I've been selling for the last 6 months or so. I've attached a series of test points, and these test points are linked to the analog discovery and 2 multimeters. This one just loves to turn off. So let me explain what's going on here. These 2 points here are injecting a DC voltage to simulate the operation of the current sensors. Over here on this inverter, where we have a similar board fitted, you will see the 2 current sensors connected in here. So we're injecting a signal here to simulate that. These 2 points here are monitoring the output of the op-amp, which basically buffers and conditions the signal before feeding it down here to the comparator. These 2 wires here are monitoring the high and the low set points for the comparator, and this yellow wire is monitoring the status of the comparator output. So this is what trips the overcurrent circuit. This is what tells the microprocessor that an overcurrent event has occurred and that it should shut down. So These bring the signal in. These monitor the signal as it's being fed to the comparator. These monitor the window set point of the comparator, and this one here monitors the comparator output. So at the minute the inverter is in a idle state, and we are connected to it with the computer over Wi-Fi. Sorry about all the wires here, it's a bit of a mess. Now at the minute we've also made some changes to the component values in the as we'll call it, the signal conditioning circuit. So if we look at our two multimeters, you will see that right now I have a low trip point of 170 millivolts and a high trip point at 3.18 volts, let's say. Now, so I'm going to come over here to the computer, and I'm hoping you guys will be able to see all this stuff. So, right now, these are my two current sensor simulators. So I'm just using DC, and I'm injecting 2.5 volts onto each one. So that basically is the condition that the current sensors have when there's no current flow. A voltmeter here, and it's just the DC part of it that you'll want to see, is showing me the output from the signal conditioning circuit. So at the minute this 2.5 volts from each of the current sensor inputs is being conditioned to read about 1.66 volts roughly on both channels here. They'll never be the same, just due to component tolerances and things like that. This logic analyzer, I'm just using the one channel, and this is monitoring the logic value of the comparator output. It's a value of 1 at the minute, so that's high, so that means that we have not tripped out. Because if we go back to the voltmeter, we can see that the 1.66 volts is in between the window of 170 millivolts and 3.18 volts. So over here on the other screen, again, I'm hoping this is going to turn out. It's probably, you know, my usual crappy camera work. But what I'm going to do is I'm going to start the inverter in manual mode here. Just want to verify that it's actually started. Oh, yes, it has. So we're in manual run mode, which is fine, and we need it to be there so that we can actually plot the current sensors. Now, what I'm going to do now is I'm going to plot my two current sensors. It's going to plot. I'm going to start the plot. And we'd see that we're basically hovering around 0 amps here. There's a little bit of jitter, which is perfectly normal. If we come back here and see that we're at 1.66 volts. So, next thing that we want to do is we want to inject the maximum swing of our current sensor that we're going to allow. So on the positive side of it, that's 4.9 volts. Now where that came from, I will explain in a minute. So let's set these up to 4.9 volts. Okay, so what we'll now see is that we are reading a current of just over 1200 amps on our graph, and our inverter is still working. Because if we look again at our voltmeter output from the signal conditioning circuit, you will see that we now have 177 and 182 millivolts coming out, and that is above the 170 millivolts lower trip point. So this means that our signal conditioning circuit and our window comparator is now working not just up to 900 amps but up to slightly over 1200 amps. As we can see here, you know, we've got a jitter here now between about 1217 and about 1224 amps, which is perfectly fine. Now, because having dead accurate current readings is not required for the Hubner control system. And if we look at our logic, we'll see that we're a logic 1. I'm just going to slow down the pace of this logic analyzer here very much. I'm going to put it on 6 seconds per division. So you'll see it's just plotting across slowly now. If we now swing our current sensors back to the minimum voltage that we'd like to allow, 0.1 volts, press enter, and 0.1 volts, and enter. We'll now see that we are just at slightly over negative 1200 amps. In fact, I should just messed up, did I? No. Come here, Bill. Come on, Bill, you can do it. Now, I'm going to stop the plot, go to the spot values, and if we refresh these, we should get a digital value of about 1220 amps. So that's fine. And we're going to start the plot again. Oh, no, we're not. Really? There we go. Plot and stop plot. Okay, so there we are. We've got about a jitter there of about 1219 to 1224 amps. Now, at this point now, if we look at our voltmeter output from the signal conditioning circuit, 3.14 volts per channel. As you will see here, that is just below our 3.17 volts for our high end of the window comparator, and thus our inverter works away quite happily. Now, but what if we go outside that? So let's take one of our channels and let's change it down to 50 millivolts. Now when I press enter, this is going to pretty much trip out our overcurrent circuit. So boom, enter. And I'm now going to go over to the logic analyzer, stop it, and you will see here a little dip. Let me see if I can zoom in on that. Not sure if I can. No, sorry, I can't. But let me see if you can see that. But that little dip was our comparator tripping and shutting down the inverter. If we go over here now, go to spot values, and we look at the op mode. We go to refresh, watch op mode, and off, because we have shut down. So what I'm going to do now is go back on my waveform generator, back to 2.5 volts here, and back to 2.5 volts here. And our window comparator now resets. We have our lower setting at 170 millivolts and our high setting at 3.17 volts. So we've had to make some component value changes in our signal conditioning circuit to make this work, and a few parameter changes, which I will now let me grab my notebook here and we'll run through what they are. So let me see here. Highly professional videography in this channel. Now, there we go. Alright, here we go. So, now you might ask me, why do I choose 0.1 volts and 4.9 volts? Well, as our trip limits, and there's a reason for that. Let me just grab something else in my highly professional video series. Say hello here to the original Tesla logic board from the small drive unit. Now let me get a little pointer here. I can show you guys something. So this is where the current sensors connect, and this current sensor programming header also brings the current sensor pins out to a point that I could connect to them. So I've been a naughty boy. I've been injecting signals and finding out what Elon does to them. Now, our current sensors come over here just through some basic filter caps, and they come into this device here, U25. And U25 is an LMV844 quad op amp. And in this case, it's configured as a buffer amplifier. And these resistors here, so these ones from R70 over to R98, are used to divide the input from the current sensors by slightly more than half, or sorry, slightly less than half. There's a 10K and a 12K resistor that are used. And this buffer amplifier then basically prevents any loading on the current sensors. Now, this is where it gets really fun, because once it comes out of the buffer amplifier, it goes into U38, this device here. Now, I'm going to give you guys one guess what U38 is. It's an LM2901 quad comparator. And guess what? It's used in the exact same way as we use the window comparator on the open source board. I'm going to come over here to these three test points. There's TP43, TP45 and TP58. And these are nominally 3.3 volts when our current sensor is within the window. And when we go outside the window, these guys trip low, just like the open source board. And they're basically fed to this TMS 320 DSP chip. Now what it does after that, I haven't, been too worried about. So we use the very same analog overcurrent detection system. And Tesla have set their trip points at 0.1 volts on the current sensor and 4.9 volts on the current sensor to trip TP43 or TP45, depending on whether it's a high or a low signal. The actual analog current values are fed in through some of these test points here into the TMS 320 also. I forget exactly which, but we'll be getting into more detail on this in a later video. But right now, what that tells us is what Tesla do. And the next question is, why do Tesla do that? Well, the current sensors that they use have a, I don't know what's the fancy word for it, transfer function or transconductance or whatever you want to call it, of 2 millivolts per amp. And they nominally sit at 2.5 volts when there's no current flow, go above 2.5 volts when there's a positive current flow, and below 2.5 volts when there's a negative current flow. And by positive and negative, what I mean is the direction through the current sensor. So, if we take 4.9 volts, we subtract 2.5, that leaves us with 2.4 volts. 2,400 millivolts, which is 1,200 amps. So, a span of 0.1, 4.9 volts is giving us a positive and negative swing of 1,200 amps. If we take the full swing of 0 to 5 volts, it's 1,250 amps. So we leave a little bit on the table to ensure that we can get a good detection. So, first thing that we need to change is the gain factor on the parameters page. That needs to be set at minus 1.5. This gives us a current reading when we're at 4.9 volts on the current sensor of 1,220 amps, as we just saw. And we're at 0.1 volts of minus 1,220 amps. What we also need to do is change some resistor values. So R44 and R49 need to be 62K, and R48 needs to be 3.16K. Now this was something that the Team A guys actually did highlight to me before they stopped talking to me, but unfortunately they didn't go far enough in their component value changes, because what we really need is the 62k in R44 and R49. This gives us approximately, as we just saw, values here within the window that we can use for the full 0.1 to 4.9 volt swing. Now, so that is what we've got going on the bench right now. So that is the test setup, and that is what we have found. Now there's one last thing I want to show you guys, and of course my newly installed Ubuntu just loves going asleep. Put my super secret password in there, because there's one other thing I want to show you guys, which is this. This is the current sensor that Tesla use in the small drive unit. It is the Melexis MLX 91209. It is a programmable current sensor and costs about €3 each on Mauser. So quite useful to know, because I have broken my fair share of these things, and so now you guys know. So that is our current sensor. This has been our test setup to determine our new component values so that we can get the full swing of the current sensors. Alrighty, so I hope you guys have enjoyed that. As promised, it was long, boring and technical. Next stage is we are going to be doing some testing, and once I have verified this, we will be in a position to confirm it to you all. And indeed, we might look at how to get some more current in there with reprogramming the current sensors. Ooh, scary. So, until then, don't forget to like, share and subscribe. Check links in the description for my Patreon and PayPal, in case you should feel the need to give me some money. Also, there'll be a link in the description to GitHub, where you can download all of these designs, including the details on the modifications described in this video. I'm also planning to do a live stream where I will answer questions and discuss in more detail some of what's in this video. So until then, try not to do anything too crazy on me. Don't get hoarse like me, because that's from talking too much. You see, when you're as self-important as me, you tend to feel the need to, well, how should I put it, to shove your opinion down other people's necks, and that'll lead to hoarseness. So, we'll see you next time, and happy component value changing.